Okay, so this problem involves a material balance conducted on a packed bed reactor, and actually multiple material balances. We have two reactions, 1 and 2. So reaction 1 is that, 2A going to B plus C, and then some of the B can subsequently react with D, which is also fed in reaction 2 to produce E and F. And so ultimately, as you can see in part B, we're going to want to find out what happens to this B that's involved in both other reactions, produced in one and consumed in the other. But along the way, we'll do some balances on other species. All right, and so the first question is, what is the concentration of A given some conditions and kinetics here, exiting a reactor containing 50 kilograms of catalyst? The first thing that we're going to find that is useful to know is a inlet concentration of A, which we can later relate to the inlet concentration of D. And this is equal to the mole fraction of A times P over RT. Right, where we can assume ideal gas law behavior because we have low pressure and a reasonably high temperature of 400 K. All right, and if we assume that, so the mole fraction of A is 0.75, because it's a 3-to-1, 75-25 mixture of A to D. The pressure in this case is 1 atmosphere. Right? The temperature is 400 K. And then the R value that we'll want to use is 0.82, which we use that because it provides units of moles per decimeter cubed. And so we get a concentration of 0.023 moles per decimeter cubed. All right, we then want to, it's then useful to set up a balance on A, since A is what we're looking for. And we see that this is simplified in a way because A is only involved in a single reaction. And it's not produced by any reaction, it's only consumed by the first reaction. And so that makes our lives easier, that we can write a balance that incorporates only a single reaction rate expression. All right, and so that balance for a packed bed reactor would look something like this in its differential form. The change in number of molar flow rate of A with respect to catalyst mass in the packed bed reactor is equal to the reaction of A. I'm going to write that over here because I'm going to fill in something else here in a minute. And furthermore, this is an ideal gas reaction, and there are no change in the number of moles in either of these reactions, so it's 2 moles to 2 moles, 2 moles to 2 moles. There's no pressure drop, and therefore not only are those numbers constant, but the volumetric flow rate will be constant, and therefore we can treat the volumetric flow rate as a constant and pull it out of the derivative, which makes the math simpler in this problem. So the volumetric flow rate comes out of the derivative, and we get a dCA dW here is equal to RA, and we're told here that reaction 1 is elementary as written, which means that it's a second order reaction. So RA is equal to negative KA CA squared. All right, now we just need to separate variables and integrate both sides of the expression. So we pull the dW over to the right-hand side. We divide through by CA squared, and what we'll end up with is our negative, pull a negative sign over here too. We can say dCA over CA squared, integrating from CA naught to CA, is equal to KA divided by the volumetric flow rate, where I pulled that term over to this side, dW. And we can integrate that from the start of the reactor, where there's no catalyst that's been seen by the fluid, to the end, where it's seen W. All right, and then, okay, now if we actually integrate that out, then we get a pretty simple expression that you've probably seen many times before by now, that 1 over CA minus 1 over CA naught is equal to KA times W times the volumetric flow rate. Okay, and now we have a nice situation that we actually know all of these numbers, and there are no tricky unit conversions here, so I'm not going to plug them in, but the volumetric flow rate is 10 decimeters cubed per second. Catalyst mass is given in kilograms as 50 kilograms of catalyst. We're given a value for Ka in the problem statement in terms of decimeters cubed, moles second, and kilograms of catalyst, so again, no need for unit conversions. And we have determined that Ca naught in this problem is 0.023 moles per decimeter cubed in an earlier step. And so that means we can solve for Ca, and I'll just write it over here in the margin, that we can solve for Ca, and I get that it's equal to 0.0097 centimeters cubed per mole at the exit of the reactor. Okay, and so we see that a substantial amount of A was converted during this reaction. Okay, now we can move on to part B. When we do that, it's useful to look at these two equations. And one thing that we notice is that it might be easiest for us if we actually solve in terms of another reactant that's only involved in a single reaction. And here there are many ways to solve this problem, so I'm just trying to look for one of the simplest ones. We could move straight to doing a balance on B, which is what we want to solve for. But I'm going to go ahead, it turns out that in this problem it's, at least to me, I think a little bit easier to solve for the D that's exiting the reactor first, and then use that to figure out how much B has been consumed, and therefore how much is left in the reactor at the end. Okay, and so again, the reason we do that is D is only implicated in one reaction, and so the math might turn out to be simpler than if we tried to track B. All right, and another reason why it really turns out to be fairly essential to try to solve for D is that we see that if we have to write the balance on B, if we look ahead, that we're going to have that being dependent on an expression that is first order in D but has no dependence on B. And so we're going to need to know how the concentration of D varies through the reactor in order to express that rate expression, which ultimately involves solving for a functional form for the concentration of D down the length of the reactor anyway. And so we'll go ahead and solve for that, and we'll see that that's really kind of all we need to do in this problem to get a fairly straightforward step to a final answer. Okay, so if we do a balance on D, okay, we follow the same form, same argument that the volumetric flow rate is constant, and so the concentration of D, dW, is equal to negative KD CD, and we're given the rate constant for that second reaction in this problem, so we'll be able to just plug it in. Another piece of information that's useful is that CD naught, you feed it in a 1:3 ratio, a CA naught, so it's equal to 1/3 CA naught, and we already, in the previous part of the problem, already calculated CA naught, and so we can find that this is equal to 0.0077 moles per decimeters cubed. Okay, and now we can go through and integrate this expression, but you'll recognize this probably right away as being a first-order differential equation that we've solved many times before. All right, and so if we integrate both sides of this expression, we get the classical decaying exponential, that the concentration of D is equal to CD naught times the exponential of our collected constants, so negative KdW over V naught. Okay, and now we again can just plug in some numbers. So CD naught we've just solved for above. It's 0.0077 moles per decimeter cubed. KD is given on the previous page. So it's given in the same system of units of decimeters cubed per second kilogram. Okay, and then get back here. Catalyst mass again is 50 kilograms, and the volumetric flow rate is the same as in part A. And again, there are no real unit conversions. You can plug this straight in to arrive at an answer. And that's that CD at the end of this reaction should be 0.0053 moles per decimeter cubed. All right, now what we could do, we want to solve for the amount of B, and we could do that by writing a differential material balance equation that related to the reaction rate. But we also, in this case, can just use the stoichiometry of our two reaction equations. All right, so if we back up and look here, we can see that we know how much A reacted, and for every mole of A that reacts, half a mole of B is formed. Okay, so we know how much B is formed from the first reaction, and from the second reaction, for every mole of D that reacts away, a mole of B is consumed. And so from that we know how much B is consumed in the reaction. And so we can just use fairly straightforward stoichiometry to finish solving this problem. Okay, and so therefore the B that's exiting the reactor is equal to the A that was reacted away, FA naught minus FA, divided by 2, because only half a mole of B is produced for every mole of A that's consumed according to the stoichiometry. And then we also know how much D was reacted. We just solved for that above. Okay, and so that corresponds to how much B is reacted away, hence the minus sign. All right, so now it's a matter of simply rearranging some of our variables. So we've been working this in terms of concentrations, and we know the volumetric flow rate, and so we can express this as a volumetric flow rate times Ca naught minus Ca over 2 minus Cd naught. We'll go ahead and carry through the multiplying the negative sign through, plus Cd. Okay, these are things we've all solved for. Again, we have Cd naught right here, Cd right here, Ca naught we solved for on the previous page, Ca we also solved for on the previous page. And so we can solve for the outlet molar flow rate of B. We also have this number from the previous page. And again, there are no unit conversions, so we can plug in and solve fairly straightforwardly for B, and I get 0.043 moles per second of B coming out of the reactor. So hopefully this shows how sometimes dealing with systems of multiple reactions, it's necessary, even though we're looking for the molar flow rate of B, right, to solve, because the molar flow rate of B doing that balance equation is going to bring in a reaction whose kinetics depend on knowing the dependence on the concentration of D, that you actually need to solve for. You need to solve material balances for other species before you can solve for the one that you want. But that the procedure for each of those individual solutions is, again, fairly straightforward.